welcome back to Advanced Organic Chemistry. We are making our way through chapter 25. So, we finished up intramolecular aldol reactions. That was lecture 17. So today we're going to focus on enones. Okay, what are enones and how do we make them? So, enone are these, what I call these like naked conjugated double bonds that go up into the carbonyl here. They're very useful compounds for organic chemistry. You will learn about the Michael reaction in a few weeks, but you can see that this is a good electrophilic center. So it's very versatile in terms of forming carbon-carbon bonds here or carbon-carbon bonds here. So this enone, I want you to think about how you can make this, just using what you know about aldol chemistry. So let's break this apart into the key carbon-carbon bond. So before that got dehydrated, this must have looked like this, right? And then if you think now to what the two molecular components look like, it's going to be comprised of acetaldehyde, there's a key carbon-carbon bond, and then the single carbon electrophilic aldehyde. So that's got to be formaldehyde. And then the question for you is, well, how can we make this compound with these two ingredients, right? Acetaldehyde and formaldehyde. And you've learned a lot, I hope, already during these last 5 or 6 lectures. And you've learned about directed aldol control, and you've also learned about equilibrium control. And you really like equilibrium control of the aldol reaction because you literally just throw everything together, add your base, walk away, and come back, and boom, you got your major product. And then you look at this reaction here, you know that this is your nucleophile when it enolizes, and this is your electrophile, and you understand the rules of electrophilicity, and that this is an aldehyde, but you know that this is like a super aldehyde because it's formaldehyde. It's super electrophilic. How do you know that? Well, you remember when we did silyl enol ether of the aldol reaction, we had a similar example. When you're using formaldehyde, you don't need to use a Lewis acid. Okay, so it's just incredibly electrophilic. So you might be saying, well, let's just mix these two together because A, this will enolize, and this will react here. And what's even better is that this cannot enolize. There are no acidic protons. Seems like a win-win situation. So let's set that up and let's go for lunch and think of what might happen inside of the round bottom flask. All right, so here's your acetaldehyde, and let's add our favorite base for these types of reactions. Sodium hydroxide, form your enolate, and you're really happy because this will not self-condense. This will react with the formaldehyde that we talked about. So that's really something special when you don't get that self-condensation happening. All right, so that comes and reacts. This will pick up a proton. And then it looks like all we need to do is do that dehydration, right? We need to do that E1cb mechanism in order to dehydrate and get that to leave. So let's do that. Let's take our base, remove the proton, set this up for E1cb. And you're really excited because now this will come down. You want this to come here, kick off the OH, and you're done. However, there's one little problem. The formaldehyde that we thought was the saving grace to this reaction because it's so electrophilic, turns out that because it's so electrophilic, that instead of eliminating, this would actually rather add another molecule of formaldehyde. Okay, well, you don't know about this because you went out to lunch and you were pretty convinced that this was, the only thing that would form. So, unfortunately, it keeps going. You add a second carbon through a second molecule of formaldehyde. This will pick up a water, just proton transfer, and now you're left with that. Very different from what you want to make. But you're still gone, and a base will now still remove this proton because it's still acidic and form the enolate. And once that enolate forms, you're going to want to dehydrate, perhaps, but again, you're going to have that same problem. You're going to have that very electrophilic formaldehyde, and it's going to react again. This picks up a proton from water. And you generate this compound here, which looks nothing like that. You've added 2 extra carbons. You haven't done any dehydration. And to make matters even worse, remember, we have formaldehyde. And formaldehyde is very electrophilic. And I've taught you this reaction where you could have like an alkoxide group or a base come in, and this can react with the aldehyde or ketone, and you didn't have to worry about that, right? Well, that was maybe a little bit of a fib on my part, because it's not completely true. Probably 99.9% of the time it's true. Now, in this case here, what I've taught you is that this will come back down, then your OH group will come off, and this is reversible, and that's indeed true. And this will happen thousands and thousands of times, so you don't need to worry about that. But the problem is that once in a while, what will happen is that instead of the O minus coming down, instead of the OH leaving, you're actually going to have H minus leave as a reducing agent. And H minus will be your nucleophile that can attack something electrophilic. Again, think back to those reducing agents that we were talking about during the chapter on chemoselectivity. So that's a little bit bizarre, right? But like I said, there's a healthy equilibrium of this around in solution, as I've shown you there. But once in a while, you'll get the hydride attacking this group here. And this happens when you have no more acidic protons. Well, let's see what's going on. So after that attacks, generate this. This will pick up proton from the conjugate acid of hydroxide. And this is your final product. certainly very different from what we started off and what we wanted to make. So, bit of a problem here. Undesired major product. And oftentimes students ask the same question every year. And the question is, well, you know, it looks like it's reacting with like a second equivalent and then a third equivalent of formaldehyde. So why don't we keep this as our limiting reagent and keep that low? And that's an excellent idea. The problem is if you do that, you're still going to have, when this reacts, you're still going to have formaldehyde present. So even if you add like a quarter of an equivalent, stoichiometric equivalent in this reaction, you're still going to generate this enolate and it's still going to react because you're still going to have a bunch of this present. Okay? The only difference is that you'll make your undesired product, but it'll be in lower yield. You'll never generate your desired enone. So the question is, how are we going to get around this problem? Because we do need to make enones, but it seems like the formaldehyde is a little too electrophilic and it's also acting as a reducing agent. All right, so one way that we're going to do this is through a reaction called the Mannich reaction. The Mannich reaction. It's a very specialized way to achieve alkylation with formaldehyde, but without all the undesired reactivity and reduction that we just observed here. Specialized way to achieve alkylation with formaldehyde. All right, so I'll show you how the Mannich reaction works. And before I draw that, here is our target compound. This is an enone, desired compound that we want to make. And you can see here that we're going to take the same approach in terms of how to construct this carbon-carbon bond. So if you use the same approach that we did up there, you can see that your starting materials are going to be this symmetrical ketone plus the formaldehyde. All right, but as we've learned, we can't just mix them together. We need a very specific directed approach, and this is where the Mannich reaction comes into play. Okay, so if we actually treat this with formaldehyde, but if we actually add some catalytic protons and if we add diethylamine, we can actually control this reaction. And what we're going to do is we're going to pre-mix this together, formaldehyde and this dimethylamine, and you know exactly what's going to happen. You're going to get the nitrogen attacking here. This will get protonated a couple times. Nitrogen electrons will come down to form an imine, and then water will leave. So what this will look like is this, which is an iminium ion. And it is also very electrophilic. Now, because we are under acidic conditions, and this is where you add in your ketone, and the dimethylamine is also a weak base, what you're going to end up doing is you're going to end up protonating. Instead of forming an enolate, we're going to form an enol, which is a weak nucleophile of the compound, but because we have such a strong electrophile, it puts us in good shape for that. and then our diethylamine. You could also just use a generic base. It's understood a weak base would be able to remove a proton to form the enol. So now the enol, which is weakly nucleophilic, comes down and it reacts at this electrophilic carbon source. So let's see what that looks like. And then afterwards, we deprotonate here to go back to your ketone, like I'm showing you right here. Now the difference is that we're not under basic conditions like sodium hydroxide, so we can't form enolates very readily. And you might say, well, maybe we could form an enol and do the reaction again. So what we do to prevent that from happening is that in a third step, or sorry, a second step, we actually treat this with methyl iodide. Methyl iodide is very much attracted to nucleophiles, and your best nucleophile is on the nitrogen. So this will react via simple SN2. I'll continue the reaction right on this whiteboard. You now have a quaternary nitrogen that is actually, is actually a very good leaving group, right? You have a positive charge here, and you could imagine that under conditions you could eliminate, form a double bond, and this would be a very good leaving group. Okay? Whereas in contrast with the formaldehyde, the issue we had was that when you form this enolate here and you wanted to remove this, the OH was really not a good leaving group. So it took the low-hanging fruit and took advantage of the super electrophilic formaldehyde, which is not what we wanted, but was what the chemistry what the chemistry sort of dictated us and led us to. So once you do this reaction, you generate this species here. And then typically in the third step with perhaps now you can add your hydroxide and some water or some kind of base. Then you can do that elimination. And if we're using base, we're going to use our good friend, the E1cb mechanism. And this is how you can generate enones. Okay, so it's through a three-step procedure. One, formaldehyde with that secondary amine to form the iminium ion, pre-mix that. Then you alkylate the nitrogen with methyl iodide to make that a good leaving group. And then in a third step, you basify it, and now that allows for removal of this proton via E1cb. And then you just have such a good leaving group that that's exclusively what you make. So there's lots of variants based on the Manic reaction. This is the main one, and we'll definitely talk about some more specialized examples in course packs and in problem sets. Okay, so that concludes this lecture on enones. What we need to do next is talk about stereochemistry of aldol. I'm going to do that another day. But for you, I don't know when that will be, but it's going to be just another continuation. So that will be lecture 19. So I look forward to seeing you for that one. Have a good day, everyone.